Hello again, this is Galen Pickett, Cal State University Long Beach, Physics 151. We're going to move into Chapter 10 using the ideas we have of the energy principle and the momentum principle in the point particle and the extended system to see what happens in systems of elastic and inelastic collisions. So it is Section 2 is the one that I want to talk about right now, 10.2. So here's the situation. I've got in the center of mass frame, so here's the center of mass, I've got a particle M1 with some momentum P, and I've got another particle, M2, different mass, but it's got to have the same momentum backwards, minus P. In the center of mass frame, the momentum of the system, the total momentum of the system is equal to 0, and this is the only way I can arrange this. So I could say that the momentum here is equal to P in the x direction, 0, 0, and here I could say the momentum for particle number 2 is minus P, 0, 0. Now these two particles have different momentum, but they've got to have different velocities if they've got different masses. So what does this look like? There's the initial state. The final state is, for an inelastic collision, the two objects are stuck together. And if they're stuck together, the center of mass is always somewhere between these two objects. If we're talking about the situation where the system momentum is equal to 0, I could always write that as the mass total times the velocity of the center of mass. If it's at rest, the velocity of the center of mass is at rest, so that the center of mass is still in the same spot. These two particles in the final state have got to be right on the center of mass, M1, M2. So from the point of view of the energy principle, what I have is the translational energy in the center of mass frame is always 0. So the initial energy of the system is entirely kinetic. Translational energy for the two pieces, and I can write that as P squared over 2m1, that's the kinetic energy of this particle, plus P squared over 2m2. And in the final state, the total energy is 0. All of the kinetic energy of the initial two states goes into the internal energy. I get an entire 100% conversion of this initial energy to internal energy, either by making the temperature increase or by compressing some springs or making little atomic degrees of freedom jiggle faster. So what I have is the change in the energy of the system. It's an isolated system, so the work from the surroundings has got to be 0. So what I have is the change of energy 1 plus the change of energy 2 plus the change in the internal interaction energy has to be 0. Change E1 is minus P1 squared, excuse me, just P squared over 2m1. Change of energy for E2 is P squared over 2m2, and then I have plus delta E internal. So I get delta E internal for this process is the most it can possibly be. It's P squared times 1 over 2m1 plus 1 over 2m2. That's E initial. All of the initial energy winds up into the internal energy, and that's exactly what you want to do if you've got, say, a proton coming this way, an antiproton coming this way, at the center of mass. You want all of this energy to go into making all sorts of other particles here. And the most efficient way to do that is with the center of mass.